let us see how to write down the expression for the electric field generated by a point charge. So here we see a point charge Q, and at a distance r from this point charge Q, we have a point in space that we are going to analyze. Now, let us assume that this point charge Q is positive. Electric field lines emanate from a positive point charge, that is, they start at the positive point charge and move outwards. So for this point charge Q, the electric field at P will be directed as shown towards the right hand side. Let us try to find out the electric field's expression for this particular point charge. Now we know that if we keep a test charge Q naught at the position of point P, then in that case the force experienced by the test charge Q naught will be force is equal to K Q naught upon R square. And we know that the electric field is simply given by the expression of the force experienced by the test charge divided by the test charge. This is the definition of the electric field. So this will be K Q naught upon R square whole divided by Q naught. So we can see that Q naught gets cancelled and we are left with the expression KQ upon R square. This is the expression for the electric field. Now note that electric field is a vector quantity. So if I define a unit vector r cap like such, then in that case I can write this down in vectorial format by multiplying the scalar expression with r cap, and thus we have the final expression for the electric field because of a point charge, which is electric field is equal to kq upon r square r cap. Note that in this particular case we have assumed the point charge to be positive. Now if the point charge was negative, naturally the direction of the electric field will be reversed. So just to remember, from a positive point charge the electric field goes outward and the electric field lines point towards a negative point charge. So the electric field starts and emanates from a positive point charge and it terminates on a negative point charge. We will study this particular phenomena in greater detail in the coming videos. Hereby, this phenomena that for a positive point charge, the electric field moves outward and points away from the positive point charge has been illustrated. So let us say if this point charge Q is positive, then the electric field at point P will be pointing outwards, away from the point charge. Similarly, if the point charge Q is negative, then the electric field will be pointing inwards or towards the negative point charge, as has been shown in this particular diagram. Now we have just written down the expression for the electric field. I will repeat what it was. The electric field was E is equal to KQ divided by R square. This was the expression for the electric field. Assuming that Q is a positive charge, as has been shown over here, the electric field points outwards at the point P. If we are to plot the electric field on the y-axis and r, the distance from the point charge, on the x-axis, then we'll get this particular plot as shown over here. This is a spherically symmetric situation. So the distance r, even if the distance r was in this particular direction or in this particular direction or in this particular direction, in any particular direction, as long as it lies on the surface of a sphere, the expression for the electric field remains the same and hence the magnitude of the electric field remains the same. Of course, the direction will change. For example, if r was in this direction, the electric field would be pointed thus. If r was in this direction, electric field would be pointed here. If r was in this direction, the electric field will be pointed here. So the electric field emanates outward from the positive point charge and it terminates on the negative point charge. This we have already seen. The plot of this particular expression is drawn over here, with electric field being on the y-axis and the distance r adorning the x-axis. The expression for this electric field versus r plot is E is equal to KQ divided by r square.